Thanks a lot. So I'm going to give an introduction to flavor experiments and foundations of flavor physics. And I would like to give these lectures in memoriam of Sheldon Stone, who was a professor in Syracuse University, who passed away a few months ago, and he was really a guru of the flavor physics in the B and the charm sectors. And yeah, I think he was working in experiments from the very beginning in the Cleo experiment, which was very relevant for B physics. He was proposing the Cleo C experiment for charm physics. He was even proposing a new experiment that at the end it was the VTEV experiment, which was at the end it was not approved, but it was very important and predecessor for LHC. And he has been decisive in many fields of the flavor physics, in semi-leptonic decays, in semi-leptonic decays, in the charm physics, decay constants, even in pentaquarks in LHC. So you can have a look in the Sun career to his career. He was during my career. He has been more a competitor and a collaborator, but we all in the flavor physics think we are going to miss him a lot. And yeah, I just want to give the lectures in memoriam of him. And my lectures, okay, there are 4 lessons. The first one, I will just introduce a bit flavor physics, and of course, from the experimental point of view. I'm an experimentalist. I will give also some a lesson or some description of the Ckm matrix during the day today, maybe later. I would like to explain rare decays of heavy hadrons, and also some lesson about mixing and CP violations. So this does not correspond to 1 hour per lesson. So then this depends a bit of how it's going. I don't know exactly which is your background. If you know a lot, if you don't know, I will need some help. So then please, you can interrupt me whenever you want. Please don't hesitate to ask questions, to have some feedback. I think it is very important that then one can do the proper lectures, and then you can also take benefit of them. So first of all, I think all of you know about the standard model of particle physics, and that it is formed by quarks and leptons. And then you have 3 different generations. And also you know that we have some intermediate bosons, which are responsible for the force, and the Higgs for giving mass to the particles. We have these quarks and leptons, and we have also the antiparticles. And with these fundamental pieces, with these fundamental particles, we are able to describe our matter in the universe and the ones that we are producing in accelerator. You have here all the hadron spectrum. We are able to know it. But it is called usually flavor physics. It is the study of the transitions between different types of particles, quarks and leptons. Usually it is more related to when we call flavor physics, and during these lectures I will be talking about quarks mainly, and which are governed by the weak interaction. Okay. I think you are going to learn a lot from Professor Grossman in the coming lectures. But you know that the standard model, it is you have several free parameters. You have 3 gauge couplings. You have 2 Higgs parameters, the Higgs mass and the vacuum expectation value. You have 6 quark masses, 3 quark mixing angles plus 1 phase, which is the Ckm matrix. You have 3 plus 3 lepton masses and 3 lepton mixing angles plus 1 phase, which is similar to the Ckm matrix, but this is the Ponte-Corvo matrix now related to the neutrinos. And all these parameters, which are free in the standard model, they have to be measured by experiments. And many of them are related to flavor. So the flavor has a real importance in the standard model of particle physics. And even if we know with our standard model, we are able to have really good predictions of the particles and the matter, there are a lot of things that we still don't understand, and that they are unknown in our standard model. You know very well that we don't have a quantum theory of gravity. We don't have a graviton. We don't have a particle physics description also for the inflation, for how the universe was expanded at the beginning in the very early time. We don't know what happens with the quarks and leptons, if they are composite particles or if they have some substructures, some the strings, for instance, the predictions. There are many theoretical predictions about. We don't know if there are some common subelements like leptoquarks, which are joining quarks and leptons. We don't understand why there are 3 families. We also don't understand what there is the matter-antimatter asymmetry in the universe. There is not enough in our world. We don't understand the cosmology. We don't know the value, why the value for the cosmological constants, or why dark matter. I mean, we don't have a candidate for dark matter. We know that there has to be something which is explaining the behavior of the galaxies, but we don't have a candidate. Also, the symmetry breaking, the electroweak symmetry breaking, the Higgs. So there are many things that we don't understand, how forces are unified, what happens with the neutrinos, what happens with their mass, with their hierarchy. So there is still a lot of unknowns that we have to investigate, and I think you are going to do it in the coming years. So for that, you know that there are 2 kind of ways to investigate. What we all want as physicists, it is to understand and to search which are the mechanisms and the particles which are able to explain this behavior of the universe. And we are all wanting to know which are the new particles, the new physics that they are going to allow to understand the unknowns that we don't know yet from the standard model. For that, you have 2 ways. One, it is just performing direct searches. All of you know the Einstein formula. So then you just have 2 beams of some energy. You collide in these beams. You create a center of mass energy. And then from that, you create new particles. This is particles created on cells. And the way that you can discover these particles, this new particle, it is just looking at the what it is called the mass plots. That I think you just ask, the only thing that you have to do it is to sum the form momentum of the particles that you are producing, and then you will see a peak, a clear peak, for instance here, and then you will discover a new particle. Okay, and this has been done. This is the way that it was discovered. For instance, the Higgs Boson in the UA1 experiment at 91 GeV, or it has been also the way that the top quark was discovered at CDF in Fermilab in 1995, and more recently, the last discovery that we have had in particle physics, it has been, you know very well, it has been the Higgs Boson, which was discovered in LHC experiments at a center of mass energy of 7 TeV, okay, in 2012. But there is another way to discover new physics, and it has been always very important in time, and it is through indirect searches. What we do then, it is what you have then, it is particles which are created of cells, and then what you have, it is evidence in quantum effects, so in the loops. And then you can measure different observables and then to check what it is going on. For instance, what will happen, I mean, if you have this kind of decays here, you can see there, you can have new particles in the process. So you can have some charginos, or you can have some neutral Higgs. Can you, any one of you could tell me, for instance, this decay here, why we know that it has to be mediated by a new particle, a new thing here? Any of you, can you tell me? This tau to 3 muons decay? Are you there?
For the conservation of momentum and energy.
Again, please.
For the conservation of momentum and energy.
Not the conservation of the momentum and energy. Any other thing? If you have a tau and then at the end you have 3 muons, what is happening there? You know that?
You have to have lepton flavor conservation.
Very good. Very, very good. Thanks a lot. So you have to have lepton flavor conservation. So if you have a tau in the initial state, you cannot have 3 muons in the final state, unless that you have anything that it is not a standard model and it is not conserving lepton flavor violation. Very good. Thanks a lot. So if you have this kind of decay, if you have this kind of decays, if you discover that you have a tau lepton in the initial state and then you have 3 muons in the final state, that means necessarily that you have something there that it has to be new. And this is the way that you can discover new particles by indirect searches. And this happens, for instance, before the Higgs discovery by the LHC experiment. This is what it was happening in the predicting the electroweak the electroweak observables. So just before the Higgs discovery, the mass that it was predicted by all the observables in the electroweak sector, it was that the mass, so this is the most probable mass, okay, that you will have it there. So, and it was kind of directing the search for the Higgs. So they were look. So at the time there was in the lab it was look for the Higgs boson was searched in all this region of the mass, and just before the discovery, the only reason that it was not checked, it was this small one, and you see that it was really around here. Okay, so this is what it is happening. So then what we do it is that we see here, this is just a kind of example. Okay, this is what we see, and this is what we think that it is. We are figuring out what we are trying to predict, what it is inside what we see. And the reality can be very different. So it is very important to perform many measurements and do many tests to check what it is going on. So for instance, if you have a BS meson, which is composed, this meson, it is composed by anti-B quark and squark, and it can decay to 2 leptons, for instance, E plus and E minus. If you are studying the number of particles that they are produced, the angular distribution where the electrons and the positron are coming out, the origin point in the detector, anything, all the information that you can extract from there, from these 2 particles in the final state, it can tell you what it is going inside, and then to distinguish between the different models that we have in the reality. So it can be just a standard model, and then you have W, and then you have a set, or you can have new particles which are predicted in several theories. Okay, so quantum effects and flavor physics is completely linked, and it is really very important to do it. I think you know also the GIM, you know the GIM mechanism. I think if not, I'm sure that Professor Grossman is going to explain. But in the 70s, what happened is that one was observing the count decay in a pion and an electron and a neutrino, but it was not possible to observe the count going to a pion and 2 electrons. And it was not understood why, if you have 2 leptons in the final state, why one it is possible and the one it is not observed. And this was what it was introduced at the time by Glasgow, Iliopoulos, and Mayani. It is this mechanism, the GIM mechanisms, saying that what you have at the end, you have a flavor changing neutral current, and they have to be suppressed, and they have to be, I mean, the way that, for instance, one of S quark, it is becoming, or it is transforming a D quark, it has to be by this process, and then you have to have some new quark in this loop. Okay, and then they predict the existence of the charm quark at the time. And this was a way to understand why this decay it is suppressed in comparison with this one. And these mechanisms also, for instance, from the count mixing and using this or looking at these loops which this new charm quark could be contributing, the Gaia, Lee, and Rosner were able to predict what was the mass of this charm just from these kind of processes. You have this, the mass difference in the counts in these kind of processes. We will see it in the next lectures, but you have there the mass of the charm quark, and from there you were able to predict, okay, taking into account the Cabibbo angle and things. So the way that it was predicted was because we were not able to predict that, we were not able to observe that, and then we were predicting a new quark here. And in fact, after this prediction in 1974, the charm quark was discovered by Richter and by Ting in Slack and 2000. You can see here, this was discovered, this charm quark was discovered thanks to a charmonium state, the Jepsi, which is a resonance of the C and C bar that you are going to hear about it during a lot during these lectures, and I'm sure that in other lectures. And this was the very clear peak that that it was produced there. You can see also here, this was so in the other experiment that it was discovered. This is the Mark I detector in an electron-positron storage ring at the Slack. And in fact, this detector was one of the first cylindrical detectors. And you can see here how colliding an electron and positron, they were able to produce and looking how this was decaying, for instance, into hadrons or into muons or electrons. They had a very clear peak, which was the Jepsa or the psi resonance, which was this state, and which has a mass about 3097. Okay. This resonance, it has been very, very important when this discovered, and in fact, this producing if now you produce this resonance through two colliding beams of a positron and electron at this resonance or a superior one, then you can create a lot of charm, and this is, for instance, how they have been worked some of the charm factories at Cornell or at China. Okay, and then you can see how well this resonance it is in the charm threshold. It is a bit higher, it has a bit higher mass, and it is able to produce D and anti-D mesons, and then you can study them. For instance, this is a transversal. I don't know if you are familiar with this kind of figures. I hope so. It is just a transversal image of the detector or one of detector, and then you can see here how it is produced, how a particle it is produced, and how it is decaying. So in this case, you have a D0 meson which is decaying into a kaon and a pion, and an anti-D0 meson which is decaying in a kaon and 3 pions, for instance. And from these reconstructed particles, you can create this nice peak. Okay, this is just about charm. And what it is explaining in the standard model, these transitions between quarks, it is the Cabibbo-Kobayashi-Maskawa mechanism. I'm not sure you have heard about it before. I don't know if you have heard, some of you. I don't know how much you know about flavor physics. You are going to learn a lot within this school. And Kobayashi and Maskawa, they won the Nobel Prize in 2008. So the Ckm matrix, so what it is happening, it is that in the standard model, the transition between the different quarks are governed by this mechanism, by the mechanism of the Cabibbo-Kobayashi-Maskawa matrix. So then you have different elements in the way that in the diagonal elements, which are just the transition between the UD, CS, and TB. These transitions are Favor, and when you are changing generation, the other Ckm matrix element, so that is the probability of these other processes, they are suppressed as compared to the main ones. Okay, so then you have a vertex here, and then it's just giving you this coupling, this transition probability. And an example that I think all of you know very well, it is just the beta decay, where a neutron goes to a proton and an electron and a neutrino. And this is just governed, if you have the diagram frame, you have by the W. And then here you have in this vertex, what you have, it is the BUD element. And this is very large. And this is what we have, this kind of beta decays in our nature. It is quite normal. Okay. So this is the Ckm matrix element. And then here what you have, or what it is happening is that you can have three processes. For instance, when you have the B going to a U, and then you have this BUV there, or you can have another processes which are much more suppressed, because you have different penguin diagrams where you have different Ckm matrix elements there. Okay. What it was observed is that it was that so in this mechanism, what it is observed is that the transitions between, or it is explained, let's say, that the transitions between the same family are favored, that some of the processes are very rare, for instance, or rare. For instance, the B, because it is changing from generations, the B to the U quark. If we need to chart what we observe is that these flavor changing neutron currents are not allowed at tree level, and then we have to proceed via loop diagrams, and then if you proceed via loop diagrams, means that you have Ckm suppression in each of the vertices. We also understand that this matrix elements have to be determined by the experiments, so they cannot be predicted theoretically, and they have to then be measured with the largest prediction. And then the transitions probability can be calculated in this framework. And if a transition occurs with a larger probability than expected, this will mean that we have some effect in the loop, some virtual effect that will mean that we have a new particle. Okay, so this is basically the idea. So in summary, what I wanted to transmit here is that we understand that the standard model cannot be the ultimate theory, because there are many unknowns that we have still to understand. That it will be a low energy effective theory of a more fundamental at a higher energy scale in the TIFR range or even higher. And what it is possible that it could happen, it is that one cannot access directly by searches at the LHC. Maybe the particles, that the new particles are so heavy that they cannot be produced, just colliding to proton beams. And then the way that it can be discovered is through this indirect way of looking at very, very carefully what it is inside the loops. And another important thing is that the new physics, the new particles that are able to explain our unknowns in the standard model, requires to keep the predictions from the standard model unaltered, because we know that the standard model, it is working well, and it is predicting many of the observables, many of the things that we have nowadays. So we have hundreds of observables that they have to be in agreement if we introduce a new particle or a new model. Okay, and the flavor mechanism in the standard model, then what it provides it is a suppression mechanism for the flavor changing neutral currents, which has been already observed and which is working well in principle until recently. Apart from some anomalies that you are also going to hear a lot during these lectures, I guess, and in the conference, which has been found, that at the moment we have not an explanation. And it is very important to measure all the observables that we can to be able to distinguish between possible new physics scenarios. Okay, so the flavor mechanism in the standard model, it is very, very important to be tested very, very carefully and with a lot of precision. And here, what I want to also to stress it is that the physics that it is performed at the LHC and the Belle II experiment, which are flavor physics experiments, goes hand in hand with direct searches, Atlas and CMS, but have larger range of accessibility to new physics in the case that these new particles are so heavy that they cannot be produced directly in just beam collisions. Okay, and another thing that I guess it is important, it is even if we have a good description for the flavor mechanisms in the standard model, I guess it is not enough elegant like model or theory. So one of the missing things that it is happening, I think, in the flavor physics sector, it is that we lack of a more or a better flavor model, which will be able, for instance, to explain of the physics anomalies that we are observing in the field that you will hear about. So I think many of you have a very strong theoretical background in India. So I think if you want to work on this sector in the flavor sector, I think it will be very good if you can try to find a new model which is able, which is more, which has less parameters and is able to describe the anomalies that we are observing. You will see about that. Okay, why we are working, or why hadrons are so important in the flavor sector, for the studying the flavor mechanism. The B quarks, it is as you know, it is the heaviest quark forming hadron bound states. You know, or maybe you don't know, but the top quark is too heavy that it is not able to hadronize. So the only so the heaviest hadronic states are composed by big quarks with a mass about 4.7 GeV, and they must decay outside the cell family. Okay, the transition have to be out of the cell family, and then that means that okay, it is kind of suppressed and it has a long lifetime. So it is about 1.6 picosecond, and this is very good for experimentalists because if you have a big quark or a big hadron, and it is produced and then has a large lifetime, that means that it is flying and it has it flies some millimeters or some quantity in the detector, and then you are able to recognize when it is where it is produced and where it is decaying to other particles. And this is very good for experimentalists. And because it has to decay in other families, you have many accessible decay channels with everyone has a small branching ratio, a small probability of the transition. And then you can study, you have a lot of channels, decay channels that you can study. So that is very good also because you can do a lot of comparison between one channel and the other. And the type of processes that you have, it is the dominant three-level processes, which are B going to a B quark going to a charm quark, which are FLAVOUR, or a B quark going to a U quark, which is more suppressed. You also have rare decays, which are flavor changing neutral currents, so that means that they are not changing charge. So then you have, for instance, B2S or B2D transitions, and the hadrons present the flavor oscillations and CP violation patterns that you will hear about also in the coming lectures. So because you have these loops there, it is the ideal place to probe new physics effects. Okay, for instance, in penguin decays. So any question till now? Or any comment? Okay. So if not, let me tell you that the big quark was discovered by the E288 experiment at Fermi-Lab. It was a fixed target experiment where you have a proton beam into a beryllium target, And this was the first indication of a big quark in a component state. This was like the jet size, so now it is the epsilon-1s resonance, which is a BB bar hadronic state, and then you can see how this peak here, it is showing in the muon spectrum. So what they were doing, it was just studying, trying to study. At that time, it was not predicted. It was just that they wanted to see if because the Ckm quark was discovered. So then they wanted to use also two leptons and then to scan what was going on. And then looking at that, they discovered this bound state of a B and a B quark, a B barrier quark. And the first measurement of the B meson, so this cannot decay in the B mesons because it is under the threshold for B mesons. But the first measurement of B meson decays were performed by the CLEO experiment, which was an electron and positron collider ring, which working at an energy a bit higher as compared to the epsilon-1s, that it is the epsilon-4s that maybe you know because you work on Belle or you have heard about Belle. And this was kind of the beginning of the B physics era, let's say. Okay, and then you can see here, this was in the CLEO using the different final states, how, I don't know, maybe there was 10 events about for each of the decay channels, and they were able to measure the mass of the P and the charge and the neutral B mass, okay, big measure mass. So some basic definitions, and that I will really like if you can tell me if you have heard about them. I think the center of mass energy, you know very well. It is the available energy for particle creation. And this depends if you have a fixed target experiment or if you have a collider. So for instance, what it is better? Anyone, I'm sure that you know, what it is better, to have a fixed target experiment or to have a collider? What it is more productive, let's say. But if you have to create a new experiment, with a very high energy in the center of mass, what would you do? Okay.
We're here, but I think everyone's a bit shy still. Hopefully they will.
I hope that because if not, because if not, I'm feeling like, okay, maybe no one is listen to me, and it is a bit boring also for me. So if any of you,
so there is already answer in the chat box by
this is
Kumar.
Also Kumar, please.
Yeah, collider. The answer is collider. Nilam also has said the same.
Yeah, you can talk also. It is good to hear other people, not just me.
Yes.
It is much nicer if we have some background. Okay, and then we are not sleeping. So exactly, in a collider, you can just do a brief calculation here, and then you will see that it is much more efficient. You can get much more energy if you are colliding. If you are collider two different bits, because you have this the energy. And you know about the luminosity. You know also about the luminosity. Have you heard about it? It is just a measurement of the number of collisions that can be produced in a detector per centimeter square and per second. And it has this definition. It is just the collision rate of the frequency times the number of particles per bunch divided by the transverse size of the transverse size of the beam at the interaction point. So as smaller it is, as much as luminosity we can have. It is measured in centimeters -2 and second to the -1. I have maybe you can do some exercise related to the luminosity and how much even we can get, depending on what we have as this quantity. And the rate, it is just the luminosity, the rate or the number of events that we are going to have in an accelerator. It is just the luminosity times the cross section. And this is, it is measured in bands, which is just 10 to the -24 centimeters squared. And maybe you are very familiar with these quantities, but it happens when I'm giving lectures in my university that when people are doing the calculations, they are missing units. And so I really advise you to just to do the exercise and then to check how things are. for the different accelerators. Okay. So let's see how the hadrons are produced, how we can produce the hadrons, the ones that we want to study for Flavor physics. So there are different mechanisms, and the different experiments are depends on the mechanisms they are produced that we have. So one of the most important ways, as we have seen, it is that from the decay of the epsilon-4 resonance, which is BB quark state, which is produced in E+ A- collision. So you know this is how, for instance, the Belle II or the Belle experiment has been. India, I think it is. There are many people working on that. And you know that it is, so then you have an electron and a positron, and then they create this epsilon-4 state, and this state, it is decaying into a B meson and a B bar meson. Okay, so this is the resonance. So you have different resonances, which are BB bar quarks state, but the one that it is producing B mesons, the one that it is over threshold, it is the epsilon-4s. Okay, and has a cross section which is about 1 point something nanograms. Okay, and very important thing from that you are going to hear a lot about it, mainly from Professor Karim Tadalsi. It is that these states, when they are produced in a coherent way. So then if you have a B plus meson, you will have a B minus meson. So it is directly the mesons which are created on cell directly. Okay, it is not that a P quark that it is hadronizing. But the B mesons also can be produced, or the B hadrons in general can be produced from the hadronization of P quarks in proton-proton collisions or in proton-antiproton. And this has been done in many of the experiments in CDF and D0, and now at present in LCB, Atlas, and CMS. At the epsilon-4s, okay, you know Belle for sure, you know Babar probably also in Slack, but they were previous experiments also, Cleo and Argus, which working in these resonances. And another way that the B hadrons have been studied, it has been from the decay of the set resonance, the set meson produced in E+ A- collisions at LEP experiments in Delphi, L3, Aleph, Opal, and also in another experiment, SLB, in the Slack linear collider. I don't know if you have heard, because they are very old experiments, so I don't know if you have heard about them, but this was also very important for flavor physics. Then you had the set which was forming the E+ A- collision and then decaying to PB par. Okay. This is how they are produced and how they are decaying. So you can have different decays. You have dominant 3 decays, which are semi-leptonic, or it can be hadronic. So then you can have leptons or hadrons in the final state, for instance. You can have rare hadronic decays with different mechanisms. You have internal spectator, you have a gluonic penguin or a WS chain. You have with different final states. We will hear about them also. And we have radiative and leptonic decays that also you are going to hear a lot about them, where you have an electroweak penguin and 2 leptons in the final state, or electroweak box. So all these processes that they are allowing, for instance, from B to, so from a transition from a B to a squark. We can also have a radiative penguin where you have an emission of the photon. We will hear a lot also about them in the coming lectures. Or we can have annihilation and have 2 leptons in the final state. Okay. So this is the way that how the hadrons are decaying. So one can produce it from set decays, from epsilon-4s decays, from proton-proton collisions, and one can study the decayments in all these channels, or in any of these channels. And how we detect them? I don't know either if you know about I don't know if your experimental background it is high or it is not. Maybe what I'm saying it is too simple for you. Then everyone knows a lot about them. But just let me to check. For instance, you have here it is just a typical structure of a high energy physics detector, where you have the different the detector in different layers. And you have here, this is a transversal image, for instance, in the case of Belle. This is what how you will see the different particles, or in the LHC experiment that has a different geometry. But at the end, what we have, it is a very similar structure. At the very beginning, at the very near to the beam pipe, very near to the interaction point, what we have it is a vertex detector, or a vertex location detector, which is the one which is able to reconstruct the decay vertices of the particles that they are decaying just very shortly. Usually they are formed, they are silicon detectors, which are very precise. Then, apart from the vertex detector very near, we have another tracking systems, which gives also from gas, or also with silicon detectors, which provide also the trajectory of the particle. We have some detectors which are related to the particle identification. We have what it is called calorimeters, which all the energy deposits are there. For instance, in the case that we have a photon or that we have an electron, we need an electromagnetic calorimeter to recognize it. Or for hadrons, we need an hadronic calorimeter. And then at the end of the detector, we have the muon chambers. What do we have the muon chambers at the end of the detector? Any one of you know it? Any one of me, you can replay? Why we are in any experiment, in any high energy experiment, why we are placing the muon detectors at the end of the detector?
It has a longer lifetime and it can pass through all this. Like in CMS, we have a iron plates just before the muon detector, and can pass through it also. So,
very good, very good. Thanks a lot. Thanks a lot. So the thing is that okay, the muons are traversing all the detector. They are interacting very few with the matter. So then you always, in all experiments that you know, in all high energy experiments, you have at the end of the detector these muon chambers. Okay, very good. And something that I have not said here, and that it is very important. If you have heard me, there is something that we need absolutely in any of the high energy experiment. What is it? If we want to, we need very good tracking detectors, that's clear, but what do we need? Something that it is not a detector, but we need it. Any of you can tell me?
magnet.
Very good, thanks a lot. Very good, a magnet, we need a magnet, and why?
For the charge particle.
For bending the particle.
Exactly, very good, for bending the particles, very good. We need to bend the particles if we want to measure the momentum and to have the properties of the particles. So
sorry, Arantza, I'm sorry, I didn't want to interject anyway, but since there was a answer to your question, earlier question about the muon, someone has answered long lifetime. I thought probably we should just clarify that is not the right answer. Muon lifetime is.
I didn't understand. I didn't understand that. Okay.
Yeah. No. What you said is, of course. It's more like the electromagnetic interaction with very little energy loss.
Exactly.
The minimum ionizing. So it's not.
I
long
understood
lifetime.
that. I understood that. So then I missed the answer. Exactly.
Yeah, it was in the chat box. So I thought of clarifying. Otherwise, people will take that wrong impression.
No. Sure. Thanks a lot. Okay. So that is the thing. Okay. So it is just not. It is interacting very quickly with the detector, with the matter. So then it can traverse all the detector. Okay. Thanks a lot. And okay, very good. And then this is all what we need, and you will see that all of the experiments that we have in high energy physics, they have this kind of structure. And thanks a lot for your replays. So then let me to tell you about some of the flavor physics experiments, the predecessor of the present experiments, which were key. You know about the B factories, Belle at Keck in Japan and Babar at Pep2 in California. They were E plus A minus colliders working at the epsilon energy. It is like the Belle II that you know, and that you will be also carrying many of these physics from the professor Travelsi. So in this B factories, what you had, it is just two different rings, two different beams, one with high energy and one with low energy. So then you were able to have a small boost. So the B mesons, the epsilon 4s was created, and then the epsilon 4s was decaying into a BB pair, BB meson pair, and they have a small boost because this asymmetric, because the beams were asymmetric. Then they have a small boost, which was favoring the process of measure the different vertices and distances. Okay, the luminosity was quite high at the time, and depending on if it was Babar or Belle, you have a different beam crossing angle, which was allowing to have more luminosity. Okay, reducing the size, the effective size in the of the beam. In the interaction point. And these B factories were really very relevant because they were performing the first measurement of the CP violation in the B system. They really do an amazing work on the measuring of the Ckm matrix elements, and it was also possible to discover one of the hadrons, of the B hadrons, which is the eta B. Also, in proton-proton collisions, in proton-antiproton collisions in this kind, it was very relevant for flavor physics. The Tevatron, maybe you have heard about it. It was from 87 to 2011, and it was in Fermilab. There were two experiments, CDF and D0. Always it is very good to have different experiments doing the same kind of physics, because then you can compare and then you can corroborate whatever it is measured. And it was a proton-antiproton collider working at the center of mass energy of 1.96 TeV. And the detectors, it was D0 and CDF. The luminosity you have here, it was 10 to the 32 centimeter minus 2 second minus 1. And okay, there was a lot of electroweak physics. There were also Higgs searches, but it was very relevant for B physics. And in fact, the discovery of the top quark was there, the first measurement of the BS oscillations, and also the discovery of the cascade B baryon, for instance. Older, but very important also, they were the experiments in the LEP and SLC, so E plus A minus collider working at the set energy, where the cross section for BB quarks and charm quarks, the B hadron lengths were measured, B oscillations, and also a measurement of the Ckm matrix element before B factories, and also the discovery of the BS of the lambda B baryon. They were discovered there. And they were just electron and positron linear collider, which was in the, so the LEP was in the LHC ring, and also was doing, and we had 4 different experiments, Aleph, Delphi, L3, and Opal, and then there was another detector, another collider in Slack, and with another detector, the SLV, which also was very relevant for this. Okay. And mainly related to Vertex detectors, and distinguish, for instance, between B and charm detectors. Let me to focus now a bit more in the LHC experiments, because and in particular in the LHC experiment is the one that I'm working on. They are the present ones, and where we have observed many of the intriguing observables in flavor physics. The LHC, the people working on CMS here, you know very well, it is a proton-proton collider with an energy of 13 TeV, and you have 4 experiments, and the one it is particularly dedicated to flavor physics. Here, I don't know if you had the chance to go to the pit and to go underground and see the one of these detectors. This is how it looks underground, the LHC detector. Okay. what it is happening, why we have this this experiment, and why we have designed in this way. So the BB bar cross section in proton-proton collisions is very large, and it is coming mainly from gluon fusion. So then you have the production. It is just forward or backward. So it is they are created. The BB quarks are created with a very low angle, with a very small angle. So you can see here, okay, how they are produced. So one then thought, okay, if we and in these B quarks, okay, that they are produced with a very small angle, they hadronize in different species. So then you have B, BS, you have B baryons with an average B meson momentum about FPGEV. So because they are so collimated, these BB quarks are so collimated, the idea was okay, but we don't build a single arm forward spectrometers in the forward direction, and which is covering a 4% of the solid angle, just a 4%, but which is about 30% of the B-atom production. So this was the idea for the LHC experiment in comparison with the other experiment of LHC, which have a cylindrical weight, cylindrical shape. And what it is, one of the characteristics that it has, a part of the geometry of the LHC experiment, that it is special. Another thing that it is also special for this LHC experiment, it is that the luminosity that we are taking, the beams in the interaction points are a bit the focus, in the way that instead of having so many interactions as Atlas for CMS have, we have less interactions, and the number of production, because what you have is you have a proton and a proton interaction, so then you have parton interaction inside, and you don't have to have many of the agents, because if you have so many tracks, that for instance in Atlas and CMS, it is much more complicated to know where the primary vertexes are, where the decay vertices are, and to suppress from the different backgrounds. Okay, so at LHC the idea was, okay, if you have the probability of having different production vertices, or the different of having different interactions, it depends on the luminosity. If we are around here, which we have maximum 2 say interactions, then we will be able to separate much more the vertices, the production vertices and decay vertices. Okay, so this was the idea. So this is the this is the LHCb experiment, and then you have the different, it is the same as I was doing before. So then this is the different, you have a vertex, at the very beginning of the detector, you have a vertex locator, or like to measure the decay vertices. You have different tracking stations, which are able where you can, thanks to them, you can measure the tracking of the particles. You have different rich Cherenkov detectors, which allow you to identify the particles. You have the magnet, which allows to bend the particles, and at the end, as we were saying, you have the muon chambers here. Okay, so you can see, depending on the particle, this is where we are going to detect each of them. Okay, just to show again that it is the same structure, and that it is really important for any of the detectors. So what do we need to be able to reconstruct and to do a good flavor physics program, to have a very good flavor physics program? Okay, we need to reconstruct the production and the decay vertices, and for that we have to have a very good decay vertex resolution and good impact parameter resolution. You know what an impact parameter it is? Any of you know?
No.
I'm reading the chat, sorry, because I am not able to read it at the same time I'm explaining, so I'm not sure. If you have any question, just interrupt me and tell me. I think it will be much easier, and I can also help. So sorry, impact parameter, you know what it is? No? So the impact parameter, it is just, we will see in a picture maybe later, but the impact parameter, it is that when you have a track, so that the minimum distance of a track to a vertex, it has the impact parameter. Okay, and then if we want to know if a track it is coming from one vertex or to another one, or from here or here, it is very good, it is just here. But in practice, maybe you have another track which you don't know exactly if this track is coming from here or if it is coming from here. So if you measure the distance between one track to the minimum distance for a track to a vertex, then this is the impact parameter. And for that, it is very good to have very good resolution. Also, what it is very important, it is to reconstruct the momentum, and it is important to have a good momentum resolution. Okay. So one thing that you can check maybe in your tutorial session, it is that how long will a lambda V baryon, for instance, be traveling in an LHC detector in particular before decaying. Okay, just considering that the momentum of the lambda V is about 50 GeV, for instance. Okay, so in the LHC we have a very precise tracking. So we have a resolution which is very good, from 0.5 to 1%. Okay, this depends on the momentum, depending on the energy of the particle that you have. We have a good impact parameter, so about 20 microns, and a very good vertex resolution. Okay, and this is very, very crucial to perform good flavor physics measurements. Also, I wanted to tell you how for instance, or just giving an example of how it is the tracking at LHC and how complicated it is. Okay, so you have different tracking detectors. For instance, you have the velo at the beginning, it's the vertex detector, then you have a TT station, you have some tracking station and the magnet that it is allowing to bend the trajectories. And we distinguish between the tracks at LHC we distinguish between from where they are coming. For instance, if they are just coming from the velo, so you have a decay here, and then you have a track which comes just in the first tracking, or if you have a very long track, which are the usual ones, which is hitting all the different detectors. So what I want to show you is that just from a simulation, for instance, suppose that you have to recognize one of the decays, one signal track, which will be given in the different tracking systems, will be some hits, some interactions there. You can see also how many hits you have from non-signal. So all these brown points here in the different layers are coming from different, from backgrounds, from different interactions that you have, that they are not belonging to the signal. This is how it is so important, even if I'm not going to talk about it, it is so important to have very good, and it is a lot of effort to have very good algorithms which are able to reconstruct all the trajectory of the particles, which are hitting the different detectors. Okay. As I told you, it is very important to have a magnet, and you have said it, you need to bend the particles. This is the magnet that we have at LHC, and which is for Tesla. And what we do, for instance, in the LHC, it is to invert the polarity to be able to study the detector asymmetry. So depending on the polarity, you will have the different charge of the particles. They will bend in one direction or the other. And to be sure that we don't have, because we are very interested in, we want to measure, we want to perform measures between matter and antimatters, and then that means that you will have different charges. And then we want to have measurements and know that, okay, this is not dependent on the detector, and that we are not, I mean, that the measurement the asymmetry that we are measuring, it is not detector dependent. So then what we can do if we invert the polarity of the magnet, it is that this is not dependent on the detector, and then you can remove many of the systematic effects that you can get in these asymmetries. Also, to recognize the type of particles, I don't know if you have heard about Cherenkov detectors, for instance, that they allow you, if you study the Cherenkov radiation that you have different rings of different radius, which depending on the radius you have a different particle, and then you are able to recognize it. So then, for instance, you can see depending on this Cherenkov angle, you have the separation of the different particles. They are very clear. You have the calorimeters, the hadronic and electromagnetic calorimeters, which they allow you to recognize if you have an electron, a photon, or if you have an hadron. the muon chambers that they allow you to distinguish between muons. So all these detectors are really very, very important. They are called also the particle identification system. You will hear about also PID systems. Okay, and you can see, for instance, with particle identification of without particle identification, which is the difference. So if you have this will be a typical signal from the rings from particle tracks. So you have the different rings, and you can see the reconstruction of a BS meson decaying into two counts. What you reconstruct when you don't have any, you are reconstructing these two counts. If you don't have particle identification and if you have particle identification, so you have two tracks at the final state, which can be the two counts. This is what you want, or you can have also pions, or you can have protons. You can have another kind of particles, okay, coming from other decays. If you don't have particle identification, you will have many of two hadrons final states, which come here in this mass plot, okay, of the two counts. And in case you have particle identification, you have a very, very clear peak of the two counts. So it is very, very relevant. It has been a real good for high energy physics experiments to have these rich detectors. Okay, and in LHC we have a very good particle identification separation. We have a very good calorimeter system, and also we are able to have good muon identification. Okay, you have what it is called the efficiency to detect a muon, for instance, it is 97%, and also we have a small probability that we are missing, for instance, we are misidentifying a pion into a muon, which is about 1-3%. This is very, very important. Okay, in general. Something that I also want to, if I have time, I think I don't have too much time, no? It's just a few minutes, 5 minutes or something. I will continue later. But let me, I think, yeah, let me to just to talk about some of the important also ingredients that we have in Flavour physics experiments in LHC, but also in any other experiment that you want to perform Flavour physics. You know, and you are going to also to learn in the coming lectures that the B mesons oscillates between a particle and antiparticle by these box diagrams. And what it is very important, it is to know the flavor of the particle at the production point. Okay, so for that, what we use in a Flavour experiment, it is different algorithms that they make use of the characteristics of the fragmentation of the quark, the charge of the decay product, or the charge related to the other B hadron produced in the collision. So what it is, you can see here an example. So you have a proton-proton collision, and there you will produce a B bar and a B quark, and each of them will hadronize in some hadron, a B or a B baryon or whatever. And then the signatures of this, the signatural characteristics, for instance, supposing that you have anti-B baryon that it is going to create a B baryon, a B0, sorry, and we have an anti-B quark, and then it creates a B0 meson, and this B0 meson, it is decaying to a jet psi and a cascade. Okay, this is the channel that we want to study. Okay, we can use, we can check some of the properties that they are from the hadronization of the B0 meson. We are expecting that, for instance, you have a lot of positive charge pions. Okay, so if you look at because this is the way that it is produced, because you have a DD bar part here. So if you check at the charge of the pions which are produced, or use its information in algorithms, you can distinguish if this is a B0 or if this is a B0 bar. Or for instance, you can check also not in the signal that you are looking for, but from the other B quark that it has been produced in the proton-proton collision. You can check, for instance, which is the sign of the lepton that it is produced, if they are leptons produced, because usually you have a lot of semi-leptonic decays. So the charge of this lepton is also kind of tagging, what it is called the Flavour tagging, which is the charge of this meson. And this is very important for many of the measurements, in particular or related to CP violation studies. Okay. And the parameters that they are kind of describing this this flavor tagging, the way that we are knowing it, which is the flavor at the production point, it is what it is called the tagging efficiency. So it is the fraction of events with a decision, if it is a B or an anti-B. And we can have also a ground tag fraction, which is usually called W or omega, let's say, which is the fraction of the tag events for which the tagging decision is ground. So what we usually what it is defined, it is we will be talking about, but just to know it now, it is what it is called the Fettig tagging power, which is this formula here, which is relating the efficiency that you have for a proper flavor tagging and the wrong misidentification of the flavor, okay, at the origin point. And then at the end, what you have it is that the number of events that you are going to have, or the sensitivity that you are going to have, it depends a lot on the tagging efficiency and more even on the ground tag function. So just for you to know, it's supposed that you have a pattern of oscillation. So you have a B baryon which is oscillating in a B0 and anti-B0. We will hear more about it, but just to know it, how this red true distribution of the pattern oscillation, depending on if you have a mistag, how it is decreasing. Okay, you have different effects, and you can see here how they are. You will see. Okay. This is just an example or a BS event into 2 muons in the LHC detector that we will be talking just for the different, and you can see how many tracks we have, how many hits we have, and how difficult it is at the end to separate between these different collisions, just for you to know. So Atlas and CMS also, they are proton-proton, so you have proton-proton collisions. The only difference is, as I told you, it is they are working at a higher luminosity. So they have, or you have, if you are in CMS, much more track as compared to LHCb. So it is much more difficult to separate the signal and the background. So you have to perform a much more tight analysis for having the signal. But you have also good momentum resolution and good particle identification. So all these kind of flavor physics can be also performed at CMS if you are working there. So I encourage you to do it because it is really a very, very interesting program if you are working there. You are going to hear a lot about Super Ckm P and Belle II experiment, which is just the upgrade of the Ckm factory, and which is taking data, and I'm sure that we are going to have very, very nice result in the coming. And I think I'm going to stop here, and then I will recombine later. That's for sure, because I think I'm over time, right?
Just Arantza, that's fine. If that's a suitable place to stop, and Yuval is here now for the next lecture or so. So, can you hear me? Yeah.
Yes, I can hear you.
Yeah, yeah.
So
there was.
Yeah, I think I will start there, so it's not a problem at all.
So there was one question in the chat about why we have asymmetry at Belle and Baba, but if we're going to talk about, if you're talking about that next, might be good to address that at the start of the next lecture.
I will do it. I will do it. Sure.
Yeah, because I see the figure here, so.
Yeah. Okay. So, very good. I'll do it.
Okay, so no, that was great, Arantza, and so are you planning to join the tutorial session, or are you?
Maybe at the end. Maybe at the end. I'm not sure if I will be, because I have to do something. But
no
I will
problem.
try to, at least at the end of the tutorial, I would like to. And I don't know if you have any question. Just you can tell me. You can put it in the chat. You can send me a message. Whatever. We can maybe discuss it in the next session. I don't know if it was too simple for you. If it was, so I mean, any of the feedback you would like to, please just let me know.
Okay. All right. So thanks a lot, Arantza. We'll